As Mike introed, I am also Mike. I was the co-founder and CEO of HyperDX. We were really excited to join ClickHouse early this year, and I think last month we had a chance to talk about ClickStack at our user conference, and I'm really excited to talk not only a bit about ClickStack if you haven't heard about it yet, but also a bit about the updates that we've been working on. I want to thank Daniel because he has basically presented a lot of what we're about to talk about, so that's quite exciting. But maybe I have a slightly different angle to it. So as Daniel's mentioned, ClickHouse definitely powers observability at scale for a number of folks. Obviously, you're at Netflix. It's really exciting to see this scale. But a lot of other companies kind of benefit from ClickHouse for their observability workloads as well. And this is not a huge surprise because ClickHouse is really good at crunching lots of data. And observability, as we've seen, is certainly another one of those problems where you need to crunch a lot of data. So before diving in further, I want to talk a little bit about why observability sucks in its current state, or at least why it sucks for now, maybe if you're not using ClickHouse. And a bit about kind of the current state of observability is we talk a lot about the three silos, right? You have your logs, your metrics, and your traces, and there might be other expanded definitions of it, but there's certainly these kind of three core pillars, as they call it, of observability. But then at the end of the day, that's kind of become three silos, right? You have a silo for your logs, a silo for your metrics, and a silo for your traces. And the correlation between these three different signals, or the clues you need to actually solve an incident, are distributed across different data stores, and correlating and bringing them together in one place is at best, you can maybe see a few of them on the same dashboard, and the engineer has to manually correlate via timestamp to figure out what is going on. Or perhaps you shell out for a vendor to give you a very expensive proprietary SaaS solution that might not scale efficiently to kind of the scale that you're running at. And at the end of the day, they're still kind of duct taping some of these products together under the hood with a nice shinier UI. And the way that we got into this mess to begin with is because fundamentally observability is a set of trade-offs. You're trading off between something that's cost efficient, that's fast at searching, so be able to find a specific point or a needle in the haystack kind of log, and also fast aggregation. So be able to build charts and be able to do like group bys and aggregation functions really quickly over large amounts of data. And really, when you look into it, there's a couple different ways you could kind of approach this. First is that you could throw all your logs into a search engine, per se. And those search engines are really great for search. So if you have like a specific ID, it's really easy to go find that specific log line. But they're really bad at being able to actually do graphs of that over time. So aggregations over time, they're really poor at when you want to zoom out. And then metrics data stores, they're not really good at searching. You can't go from a chart down to the individual event that kind of emitted that log line to begin with. But they're really good at kind of graphing over time. So you're kind of stuck with two different data stores that are good at one thing, but not good at the other. And at the end of the day, you kind of have to like duct tape them together. And a more like concrete example of why this is a little bit limiting is we could talk a little bit about an example. Say like you woke up in the middle of the night, there's a bunch of errors going off because one of your metrics for errors are kind of going crazy. You don't get too much information about why this is happening. You just get to know like, hey, there's a lot of errors, and you get some low cardinality information like the region, maybe the node, and some other information. But you don't really know why it's happening. And then you might hop to your search database, for example, and in your search database, you're going to get like billions of results. And that's a lot to sift through. And it's hard to tell, what are the actual trends? Like, what are the new types of errors that are happening in the system? And it's really hard to be able to tell this off a search database because the graphs will be really slow to load. And really, to get true observability, you need a system that can go from your individual events to be able to build kind of trends and charts to be able to show your hypothesis is proven at scale, and then maybe find another novel insight, zoom into a specific event again, and repeat that motion until you find the exact kind of root cause that you're looking for. So really, true observability, I think you need fast aggregations over high cardinality unsampled data, so basically that original source events. that's still cost efficient at scale. So I think true observability really needs ClickHouse. And of course, I'd be saying this at a ClickHouse meetup, but you have to hear me out here, right? As I said earlier, observability is just another data problem, and ClickHouse is incredibly well suited for big data problems. It's really fast and real-time efficient in terms of searching, sub-second searches on petabytes of data, as well as on inserts as well. It has really great compression ratios, be able to compress up to 10x more data able to compress your data by 10 to 100x, so you could have leaner hardware footprints. It also supports compute and storage separation, so you can scale your searches and your storage independently from each other. It's also built on top of open standards, such as it's ANSI SQL compatible, and it's also compatible with a wide variety of ecosystem tools like OpenTelemetry. And then lastly, it also supports open formats such as Iceberg, Delta, Parquet, et cetera. So kind of no matter where your data is stored and what format, you can use ClickHouse to query it. But there was something missing of all of this. ClickHouse is a really amazing data store, but what was missing was a native user experience for observability. And that's why we joined ClickHouse at the beginning of this year to build this out. HyperDX, we've been building a ClickHouse-based open source observability platform for a number of years before joining. So really excited to be part of the ClickHouse team. And we're really excited to talk about ClickStack, which is our kind of open source, high performance observability stack powered by ClickHouse as its core data store, and then using OpenTelemetry as a way to get data in, as a recommended way to get data in, and then HyperDX, which is the UI layer on top of all of it. It's something that you could deploy in seconds on any ClickHouse instance, whether that's an existing ClickHouse instance that you already send all your data to. Like if you're Netflix, you might have a lot of data already in ClickHouse, but you might be interested in a different UI. Or if you want to stand up a new ClickHouse instance just for observability, you could set it up with the out-of-the-box schema that it comes with. It also gives you end-to-end observability from your front-end application down to your infrastructure metrics and everything in between. And all the components of the stack are being maintained in-house here at ClickHouse, so you know that you're getting the most performance and as optimized as you can get it for the kind of queries and workloads for observability on top of ClickHouse. And then lastly, it is built on open standards, so we heavily recommend OpenTelemetry. It's not the only way, but we definitely recommend OpenTelemetry, and it's fully open source as well, so you can run it anywhere you want. And I'll do a really quick demo. And this is funny because I feel like the demo is going to look really similar to Daniel's demo. Because at the end of the day, we're kind of doing the similar, we're trying to achieve similar things, so it's kind of nice that we've kind of converged. But you could also kind of play with this at home if you're interested in it. Here we have the UI. This is looking at our logs that are coming through. And one of the workflows I like to show, which is kind of similar to what Daniel showed earlier, is say, for example, one of our teammates told us, hey, like in the last couple hours, we've been having these increased elevated error rates. So let's go last 12 hours. And let's go look at our errors here. So all this is being powered on top of ClickHouse. And we'll see, hey, we have errors. And we certainly have a lot of errors. And me as a human, I would have a really hard time trying to figure out what is a novel issue, right? Usually our system always has errors. That's kind of an inevitable part of running a noisy, complex system in production. But there's clearly something new that happened in the last few hours that caused this rise in errors. So one thing that we have really neat is something called event patterns. That's something that was kind of shown a little bit earlier. It's the same concept where instead of going through individual errors, we can actually see the patterns of errors that are occurring. And this isn't just hard-coded to group by the exact message. We actually do some pattern mining as well. So it will wildcard out things like numbers and other values automatically and try to group together similar logs without you having to define any regexes ahead of time as well, which is kind of neat. And we can see here that obviously there's one error that is both happening a ton and also started happening as soon as kind of the general spike started happening. So we could go and click in, view the specific instance. They're all the same in this case. Go click in the specific log. And here we'll see one specific log line. And usually the log line by itself is not very helpful. Like knowing the Visa cache is full, it's great, but doesn't give me a ton of insight into what's going wrong. One thing that's really nice about what I was talking about earlier is that if you have all your data correlated in the same data store, we can easily join that with the traces that we're also sending into ClickHouse. And here I quickly move from the log, individual log message, into the entire trace. So you can see everything that's happening from the moment the request is generated. In this case, is a demo, so this is coming from a load generator, but down all the different microservices it's talking to. And actually, right next to this log, we have this really helpful error span that comes as part of the trace. And we can take a look at, not only is the original message, we also have some nice code context in this specific case to see, where's the origin of this error and what's actually happening. The other nice things as well beyond just traces is we also send our infrastructure metrics here. And because we're running on Kubernetes, we already know, hey, this log line came from this pod, which is running on this node. We can pull out the pod metrics, the pod events, and the node metrics as well. And we can kind of confirm that the infrastructure is healthy. In this case, it is. So don't bother SREs. Go and take a look at what's wrong with their code. But that's kind of like a quick view of the ability to correlate a lot of this information together. We also have things like session replay, and a few other neat features I'll just quickly tab through in the interest of time. We have this really cool kind of like high-cardinality span analysis. You can see like outliers of correlation between outliers and inliers. We have, what is next? We have alerts. I don't know why that didn't render properly, but there are alerts. You can set threshold, alert you via webhook and whatnot over a period. And also we have some nice out-of-the-box dashboards. This is one for Kubernetes. We have one that's more APM-like, another for ClickHouse, and et cetera. So we have some really nice, basically out-of-the-box features, and also probably a lot of nice, overall kind of nice workflows for folks that are used to observability tools to run that on top of ClickHouse. All right, so I've actually talked a bit about this before, and I want to take a moment to talk about some of the updates we've been making to the product. And from June, one of the biggest things we've been working on is JSON type support. So as Daniel mentioned, there's this really cool new type called JSON, I believe. It was first GA'd in 25.4, if I remember correctly. We're now at 25.6, so it's been a bit. There's a lot of improvements being made to it constantly. And now the entire ClickStack that I showed earlier now supports JSON type. And just kind of talking a little bit more about, what is JSON type? This is, again, a bit of a refresh of the last talk. But originally, if you're using the OpenTelemetry schema that we currently include inside the OpenTelemetry collector, or if you kind of read ClickHouse blog posts, you'll probably be running a schema very similar to this, and that's what Daniel showed earlier as well. You'll have a map that has a low cardinality string, and it maps to another string. So that's kind of where things are today, and that's how you store dynamic properties that may or may not exist in an event at a given time. But there's a few problems with this map type. One of the first ones is wasted I/O, as Daniel was mentioning. Like the map type, when you're searching on it, can be a little bit expensive. It does do a linear scan over the data, and that inevitably adds significant I/O overhead. So usually to combat this, you might be materializing out specific properties in a map. You might be doing map sharding, for example, which is another great way of doing it. But basically, there's going to be some overhead to manage minimizing the I/O usage of your map types. The second problem is also a loss of precision. Because we're casting everything into a string, whether it's a uint, int, a float64, or anything else, it has to get casted into a string and then recast it back to its original type that you wanted to be able to actually get the data back, which can lose precision in the process and, of course, adds additional casting that you might not want. And the last part is also about nesting. So say you have something that's like a.b.c, so like a deeply nested property. You only get, with the maps, you kind of have to manage that on your own. You only get one level of a map by default in ClickHouse. Versus in JSON, you can store a.b.c and then query back as a.b.c, and it'll work perfectly fine without any extra work needed. So the new schema would look a little bit like this. It's really simple. Instead of having that map of string to string, you just specify JSON. And then ClickHouse will now do the rest for you. And the big thing here is that the JSON type is a lot more performant than before on semi-structured data compared to the map type at search time. So a big thing is that there is a lot lower resource utilization, so you could deal with basically scanning for an exact property a lot easier. Typically, it's also, you don't have to manage nested fields, so a.b.c is naturally supported, or any sort of arbitrary depth basically is completely supported. And the data is actually stored in its original format as well. So whatever format, whether it's like a uint, an int, a float, a string, a bool, it all gets preserved and stored as that original type, which again kind of maximizes performance when you're doing searches on top of it. And then you don't have to resort as often to the kind of tricks originally with maps, both in terms of materializing the specific property in a map or sharding maps or some of the other kind of management techniques to make maps performant. And one of the things to talk about is what is the JSON? What is the JSON type actually? And the big thing that we do is that basically for every property, we will try to store it as its own column effectively. So instead of having everything kind of stored in one massive column, it will try to take the paths that you have and store them into individual columns. So every single property will have its own column. And then it also supports a new syntax for querying it. So it's a little bit easier to query as well. So instead of having to do kind of the weird kind of map string indexing syntax, it feels a little bit more like querying JSON like you might be used to normally. And then talking a bit about the field explosion problem as well. So as was shared earlier, when you have a lot of different type of properties, eventually you only have so many columns you can add. You can't add like a million or a billion columns in ClickHouse. It just won't be as performant in that case. So inevitably, eventually you'll have more properties that can store into individual columns, and it'll spill over into something that is called shared data. It's something that you can control. You can pick how many dynamic paths that you have. The more columns you have, eventually that's going to get more expensive over time. So I think by default it's 1,000, but you can tune that yourself. And one of the things to point out as well is that those 1,000 properties aren't fixed for the whole table. It is actually only fixed at the part level. So if your part has only 1,000 properties, unique properties, but your table might have millions of properties because there's a lot of parts, those will still all get stored into their own column instead of being overflown into shared data. So it's not just, you're not just limited to like 1,000 properties over the entire table. And one thing I want to do is a bit of a demo to show you the performance of the two types. So okay, so that did not reorder the way I would have liked. Let's try to reorder this. Okay, I think this will be close enough. We'll just do that. Cool. So on the top, I have basically the ClickHouse instance with the new JSON schema. And at the bottom, this is the old map-based schema. And I'll do a search on top of this. And this is a test data set. That's why the properties look a little bit weird. But it's kind of the easiest way to generate a lot of data on your own computer. So let's try this search. So this is the JSON type. It scanned. It took 0.09 seconds. It scanned only 9 megabytes of data. So a little bit small of a test data set. But let's go try this on the map data type. And you'll see that it took 0.45 seconds and need to scan half a gig of data. I think if we try like a different property, we might get even worse results. So let's try, I don't know, like 107. Let's try doing something else. Try to get out of this autocomplete input here. So yeah, so that one scanned a little bit more data than before. And then we can try, what is it, 107, something like that. So between 0.17 seconds scanning 9 megabytes and then 1.04 seconds scanning over a gigabyte. So that's kind of the efficiency that you get on the new JSON data type. It's scanning a lot less data. We're able to return results a lot faster versus the old map data type. You'll be scanning a lot more data. Correspondingly take a bit more time to actually return it all. So hopefully that's a compelling demo as to why the JSON data type is something worth taking a look at. So it's already available in ClickStack. So if you have the latest version of ClickStack, you just have to add a few beta flags to enable the feature. That will enable inserting and reading in that new schema. And then otherwise, there's a ton of other features I didn't get to talk more about with ClickStack today, but hopefully you'll get a chance to try it out yourself or go on the website and take a look to all the other really neat features we have built into it for observability on top of ClickHouse. All right, and then one of the last things is what's ahead for 2025. The first thing we're working on really soon, actually, is to bring the UI I just showed to work on top of ClickHouse Cloud. So if you're an existing ClickHouse Cloud user or customer, you can actually use the UI directly within ClickHouse without having to host anything in open source. Another thing that's really exciting is PromQL support as well. A lot of folks like to query PromQL metrics. That is coming on the way. I think there's already some stuff happening in the open PRs you could take a look at as well. All of this we also want to have fully hosted into an opinionated vertical cloud solution. So if you just want to store your logs, metric traces into a specific cloud will have that kind of stood up for you, so you don't have to kind of piece together pieces from the open source side as much as you do today. And there's other exciting things like inverted indices, anomaly alerts, a Terraform provider on ClickStack, and a whole lot more coming for this year. So yeah, that's pretty much it for everything I have today. You can get started today at clickhouse.com/O11Y, or you go on the website, go look at the observability use case. You'll find everything I talked about here and more. Thanks so much. That's a really good question. So the question was, does this only work for Kubernetes, or does it work for other services like if you're running a serverless or something else that's not Kubernetes based? So it absolutely does. The data that we pull in is all via OpenTelemetry effectively. You can pull it through other formats as well, but OpenTelemetry has support for all those different platforms, and therefore you can get that data into ClickStack and visualize it appropriately. Yeah, so it definitely works beyond Kubernetes. Yeah, that's a really good question. So what happens with the dynamic column is that it tries to pick the columns that have the highest density of values. So it's unlikely for it to be sparse. And actually, it will have better compression because those the values there are going to be more similar. Versus in a map type, you can imagine linearly, every value is going to be different, and therefore compression can only do so well. So there's actually a couple of benefits. Now, of course, if you get really technical, the JSON type has type discriminator, which is some metadata associated with the column that might add a little bit of overhead. But overall, the JSON type should be more storage efficient. But of course, it'll compress better because, for example, if you have int32s, you'll store them all as int32s, and then if you have a run of int32s, they're going to be probably easier compressed than a run of serialized int32s and then strings and everything kind of jumbled together.
Perfect, thank you. How does the JSON data type handle same key, different types?
Yeah, that's a really good question. So I was kind of talking a little bit about that earlier, where there's actually a, let me see, I think it's this previous column. There's actually a type discriminator. This is more of an artistic showing of it, but basically it will store the float32 separately from your int32 and actually separately from your float64. So every single type would have its own column. And there's actually some metadata storing what type the property is. Yeah, that's a really good question. So the question was, if you have multiple different types, say you have ints and floats, and you're trying to do a pretty trivial kind of aggregation together like a sum, what would happen with the JSON type? So I believe if the types can be coerced, so if the column only has ints and floats, for example, it will work by default. Otherwise, you will have to cast it or do a filter on top of the values to make sure you're only getting the int and float versions. The other thing you can do is you can also do, you can specify which type you want. So say I only want the int32 versions of this property. You do :int32, and that will get just the int32 values out for that specific property. Oh yeah, does the tool have any AI capabilities? It doesn't right now. That is something that we're definitely looking at. I think we have some nice POCs around, but nothing we're quite ready to ship just yet. Yeah, so here you'll have say for example, you have a lot of different properties. So sorry, the question was, say you had a type that was really rare. So I'm assuming a path, that you have the same path, but two different types for that path. Okay, got it, yeah. So you have the same path, but two different types. One of the types is a lot more rare than the other. How does JSON handle it? So in this case, we basically promote the most common path and type combinations effectively to the columns. So if you have a lot of different properties, then the rare type path combination we put in the shared data. So it'd be put into one column that's binary encoded with everything else that's overflowing. If you have only 100 properties total, it'll also get promoted into its own column. So you do get to pick kind of the number of paths that you want that can be promoted. So based on how you tune it is how it would get promoted, or I guess demoted to shared data. Yeah, that's a really good question. Can you age data out into Parquet? I actually don't work so much on the data lake part of this, so I don't have a good answer for you. I don't know if anyone from the ClickHouse crowd does. I believe the answer is yes, but I don't want to, on the record, speak falsely about it. I don't know if anyone.
You can export the data.
Okay. Parquet. Yeah, and just to repeat for the mic, you can export it in Parquet, but you cannot read it back in ClickHouse in the Parquet format. So good for archiving. Thanks, Tristan. Awesome. All right. Well, if nothing else, thanks, guys.
Thanks,